Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I'm your host, the Dabbling Doggo.
I dabble.
Last week, we learned about functions and how they are the primary building blocks of programming in Julia. Today, we'll take a look at some of the features that make Julia, well, Julia. Until now, all of the tutorials could have applied to other programming languages. Sure, there may be some slight differences, but in general, I was teaching you how to program, and not necessarily how to program in Julia. Starting today, we'll start leaving the other languages behind and start digging into what makes Julia different than other languages. Today, we'll explore how functions can use different methods, and how Julia infers the different methods through a magical process known as multiple dispatch. In addition, I'll teach you how to create composite types. Learning this skill will greatly enhance your capabilities in Julia. We'll also take a look at a style guide. A style guide is about more than just looking good. Conforming to some style guidelines will help you make your code more readable, which will allow you to collaborate with the greater Julia community. With all of these new tools, you'll be well on your way to creating your own amazing programs in Julia. Let's jump into Atom. Did you get an error when trying to start Atom? If you didn't, don't worry about it. I'm on a Windows PC, and I get this error from time to time using Atom. I'm not sure if this is unique to Windows or if other operating systems also experience this. If this happens to you, don't panic. It is an inconvenience, but it's not the end of the world. Before you do anything else, try the standard approach from the IT guys. 1. Reboot your computer. Did that fix your issue? If not, go to step 2. 2. Uninstall Julia and Atom, and reinstall Julia, Atom, and Juno. The instructions for how to install Julia, Atom, and Juno are provided in tutorial number 1. Did that fix your issue? If not, go to step 3. 3. Delete your shortcuts and rename your Atom and Julia directories. There are 4 directories to rename. Here are the directories on my PC. Replace my username with your username and rename those folders. Reinstall Julia, Atom, and Juno. The detailed instructions for how to install Julia, Atom, and Juno are provided in tutorial number 1. Unfortunately, you'll have to redo all of your settings in Atom. You can view these temporary setbacks in one of 2 ways. 1. You can throw up your hands into the air and decide to call it quits. Or 2. You can view this as a slice of life on the frontier of knowledge, where everything doesn't always go according to plan. Your positive mental attitude can make the difference between whether or not you continue on your adventure in learning. I would encourage you to keep on going and not let these minor setbacks turn you off. The road ahead of you is long and full of wonder. There is still so much more for you to explore. Don't give up now.
You can do it!
A function can be implemented differently depending on the type of argument presented. For example, in Julia, 1 plus 1 is different than 1.0 plus 1.0. The first example is adding 2 integers, while the second example is adding 2 floating point numbers. In Julia, these 2 different scenarios are called methods. The way to find out all of the methods that are available for any given function is to use the built-in function called methods. This is the list of all of the available methods for the plus operator. In Julia version 1.5.2, there are 187 methods for the plus operator. You can find out which method Julia is calling by using the @which macro. A macro is like a mini program. On the surface, macros resemble functions, but they perform very differently under the hood. I'll go into more details about macros later in this tutorial series. For now, just note that macros are invoked using the @ sign immediately before the macro name. You can see there are 3 different methods used in the 3 different scenarios. The act of calling a particular method is called dispatching. A function can have many different methods, as we saw in the example of the addition function. The process that Julia uses to select which method to use from the list of the available methods is a process called multiple dispatch. Multiple dispatch is a magical process and is made possible in Julia thanks to the gifted designers who have created a sophisticated type inference engine that works behind the scenes as soon as you hit enter. Julia allows the dispatch process to choose which of the function's methods to call based on the number of arguments given and on the types of all of the function's arguments. This is different than other languages where dispatch occurs based on the first argument while ignoring the rest of the arguments. Using all of the function's arguments to choose which method should be invoked, rather than just the first, is known as multiple dispatch. Not only is Julia able to identify the correct method without being told, Julia does so by looking at all of the arguments with little or no performance hit. This is where the real magic is, and it's one of the secrets that makes Julia such a fascinating language. When creating your own function, you have the opportunity to set up different methods for your function. This is done by using the : type assertion operator to assert that an argument in your function is of a certain data type. You can have multiple methods for the same function, and it's even possible for that same function to behave very differently when using different data types. Let's set up a generic function to test out different methods. Let's call our new function. Now let's set up our first method for our new function by using the : type assertion operator immediately following the arguments. Let's assert that both x and y are of type integer. The data type integer is called an abstract type, since it includes all of the different types of integers tracked in Julia. The specific data types like int64 and int32 are called primitive types. These are the concrete types and are included within the abstract type called integer. Now let's call our function. Notice how our function behaves differently when x and y are both integers. Let's add another method to our function to handle floating point numbers. Like the data type integer, the data type abstract float is an abstract type which includes all the different floating point numbers tracked in Julia. Float64 and float32 are examples of primitive types, which are the concrete data types included within abstract float. Again, let's call our function. As you can see, our function behaves differently now when x and y are integers versus when x and y are floating point numbers. Let's set up one more method to handle strings. Let's call our function. Now, your function behaves very differently depending on the data types entered as arguments. You can list the different methods that you have established by using the methods function. You can check which method is being used by using the @which macro. You can also see the different methods listed in the Workspace panel. Recall from last week's tutorial, when we created our own custom functions, we did not set up any methods. We simply created generic versions of our functions, and they work just fine. So why do we need to define methods for our functions? Well, in general, you do not need to set up different methods for your function. If you want your function to behave the same, regardless of the data types entered as arguments, just let Julia work its magic for you. However, if your function requires a specific data type, or if you want your function to behave differently depending on the data type, then setting up different methods is a must. When considering whether or not to set up different methods, you need to strike a balance somewhere between being too vague and being too specific. This insight will come with experience. For now, just know and appreciate that Julia's built-in type inference engine and multiple dispatch capabilities makes programming in Julia easier, whether you're a beginner or an experienced programmer. In Julia, there are three main data types: abstract, primitive, and composite. We just saw examples of abstract and primitive data types. The data type integer is an abstract data type, while int64 and int32 are examples of primitive data types that fall under the abstract data type called integer. Both abstract and primitive data types come included with Julia, and users should not need to modify them. However, there are instances when it would be convenient to have a user-defined data type. In Julia, a user-defined data type is called a composite type. A composite type is a collection of named fields that can contain a value. Composite types are the most commonly used user-defined type in Julia. Before we look at some examples, type in exit to start a new Julia session. Composite types are created using the struct_n format. In this example, my type is the name of the composite type, while x, y, and z are the named fields. The convention is to name your composite types like the built-in abstract and primitive types. That is, start your name with an uppercase letter and use camel case if using multiple words. Camel case means writing words without spaces in between and using an uppercase letter to separate the words. Unlike other languages, names using camel case in Julia start with an uppercase letter. Also, when asserting types, the convention is to use abstract types rather than primitive types. Notice that my type is of type data type. You can view the named fields by using the field names function. Notice that the named fields are of type symbol. In order to populate your new composite type with values, type in the name of your composite type immediately followed by parentheses, and enter the values as you would in a tuple or a function. When a type is applied like a function, it's called a constructor. Notice that the data type of the variable mt is of type myType. That's your composite type that you just created. You can access the field values using the variable name followed by a dot followed by the name field. Notice that your composite type is constructed similar to a dictionary. Rather than using the DICT constructor, you use the name of your composite type immediately followed by parentheses. Also, you do not have to enter in separate keys as you would in a dictionary, since you have named fields in your composite type that act as the keys to your values. Because the named fields are of type symbol, you can access the values by using the dot notation, just like you would with a named tuple. Let's set up a dictionary, a tuple, a named tuple, and an array with the same data and see how much memory they use compared to your composite type. As we saw in a previous tutorial, the dictionary takes up the most memory, and the tuples take up the least memory. Your composite type does take more memory than the tuples, but it uses a lot less memory than the array. The lesson here is that if you need a container to hold some data, and the tuple is too restrictive, but you don't need all the bells and whistles of the array, then it makes sense for you to set up your own composite type. Like tuples, the composite type is immutable by default. However, unlike tuples, you can create mutable composite types simply by using the keyword mutable before the keyword struct in your struct_n block. Construct your mutable composite type, just like before, using the composite type name, immediately followed by parentheses. Now let's try to make some changes to see if it works. That worked. That worked too. That didn't work, because you asserted that the name field y must be of type integer. That worked because 100 is an integer. The reason why you could change the name field x from a string to an irrational number is because you did not make any assertions regarding name field x. So Julia is using the type any for name field x. Let's try to change name field z. That worked because 0.1 is a floating point number. In order to see the contents of your composite types, simply type in the variable name. Or you can view it in the Workspace panel. Let's take a look at a more complicated example that will reinforce what we learned about composite types and methods. Before we begin, type in exit to start a new Julia session. Let's set up 3 new composite types called pet, dog, and cat. Now, let's set up a function called tellMeAbout with 2 different methods. Let's construct the composite types by loading values to the name fields. Notice that you can use the constructor for the composite type pet as a value in the constructor for the composite types dog and cat. Now let's call the function tellMeAbout to see how it works. Let's recap what just happened here, since there's a lot to unpack. Rather than using a standard data structure like a tuple or a dictionary, we opted to create our own composite types because it allowed us more flexibility than a tuple and used a lot less memory than a dictionary. Next, we set up one function with 2 methods so that it would behave differently for a dog or for a cat. With each method, we interpolated different values from different named fields from our composite types by using the dot format to access the values. The result is a surprisingly sophisticated data storage and retrieval tool created in just a few minutes and written in only a few lines of code. Let's run through the data to get comfortable with how Julia is storing and accessing the values from your composite types. Notice that you can combine the dots to refer to a value in a different composite type, like eggdog.id.weight or bongocat.id.age. Also notice all of the information displayed in your Workspace panel. I know that this is a lot to take in, so this may take some time to get comfortable with. However, hopefully you can see the power of using your own custom composite types, combined with using different methods for your custom functions. The last topic for today is style. For some, style may not seem as important as other topics, but remember that Julia is a language, and, like other languages, one of the primary purposes of a language is to communicate your thoughts and ideas with other people. Julia is a very flexible programming language. It will generally work regardless of how you choose to input your code. Coming up with your own style may seem appealing. However, having a unique style makes it difficult to share your work with others, and it may make it more difficult for someone to help you when you run into a problem. With that in mind, the following are some guidelines from the GitHub repository of John Miles White. The link is in the description below. He includes a disclaimer that his style guide has not been updated in years. He recommends following the official style guide found in the Julia documentation. With that said, I still think that his style guide is an excellent place for beginners to start, since not all of these guidelines are included in the official Julia style guide. You can read through his style guide at your leisure, but here are some highlights. Never place more than 80 characters on a line. Always include a single space after a comma. Never insert a space before a comma. Always insert a single space before and after an operator, except for the caret and colon operators, which never have spaces around them. The spacing before and after rule applies to keyword arguments as well. Here are some highlights from Julia's official style guide. A link is provided in the description below. Avoid writing overly specific types. Use naming conventions consistent with Julia base. Type names use capitalization and camel case. Functions are lowercase with multiple words squashed together. When necessary, use underscores as word separators. Conciseness is valued, but avoid abbreviation. While no language is truly universal, in an ideal world, a user of Julia should be able to read the code of any other Julia user, regardless of their native language. Adhering to a basic set of style guidelines will help to lower the native language barrier and make it easier to share knowledge around the world. Well, that's it for now. Today, we started to learn what makes Julia, Julia. We learned about the magic of methods and multiple dispatch. We learned about composite types and how to create our own custom data types. Finally, we looked at some style guidelines to help us adopt some best practices so that we can join a broader Julia community made up of some very talented visionaries. Next week, we will wrap up part 1 of this tutorial series by learning how to use a text editor, how to apply debugging techniques, and how to access Julia's package ecosystem. Finally, we'll go through a demonstration of Julia's plotting capabilities and end part 1 with some visualizations. So stay tuned for that. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you have any questions, please post them in the comments below. Feel free to spread the word by sharing this video, since I'm sure you'll all agree that this is the finest tutorial on all of YouTube.
Worst tutorial ever.